So first, I just wanted to say thank you all for coming. I really appreciate you taking the time to listen to my presentation, and thank you to the there we go. And thank you also to the organizers of the seminar for this amazing chance for all of us postdocs. I know that we definitely appreciate the exposure. So today I'll be talking about the work I've done over the past few years while I've been a postdoc at Michigan State University. And so the projects that I've been focused on over the last few years have really been related to neutron capture constraints for the astrophysical eye process. So there we go. So I'll begin my presentation by talking about, a broad overview of neutron capture nucleosynthesis. And then after that, I'll go into, what exactly is the eye process and how we can apply some indirect neutron capture constraints for eye process nucleosynthesis using the beta-Oslo method. And then after that, I'll talk about two classes of experiments, one at the NSCL to constrain the neutron-rich molybdenum isotopes, and one done at Argonne National Laboratory to constrain the neutron-rich barium. And after that, I'll give a summary and an overview and outlook. So to begin, just to get us all on the same page, we have our chart of the nuclides that's shown here with proton number on the y-axis and neutron number on the x-axis. So we have all of our known nuclides, both the stable ones that are shown in these black squares, and then everything that's unstable, color-coded here in yellow, and then some of these proposed isotopes in green. So every few years, the nuclear science community comes together in order to develop the long-range plan for nuclear physics, where we try to address, what are the different questions that we hope to answer over the next few years. So in the last long-range plan, we came up with 4 big questions. And so the first one is, how did visible matter come into being and how did it evolve? Number 2, how do protons and neutrons organize themselves and what phenomena emerge? Number 3, are the fundamental interactions that are basic to the structure of matter fully understood? And number 4, how can the knowledge and technical progress provided by nuclear physics best be used to benefit society? And the answer to each one of these questions to some extent can be answered with the study of radioactive isotopes. But really my research that I'm going to talk about today is really trying to answer in some part this first question about how visible matter came into being and how did it evolve? And so what we're really trying to answer is, how did we get all of these nuclei and what is the origin of the elements? And so we sort of understand that for nuclei that are lighter than iron, they're formed in some sort of fusion process, whether that's the PP chain or something like stellar burning. But once we get up to iron, we really start to ask the question, what is the origin of heavy elements above iron? And so the answer to that question, at least on the neutron-rich side, is that they're formed in some sort of neutron capture process. And so very close to stability, we have the S process, or the slow neutron capture process. And so this happens sort of right along the valley of beta stability for neutron densities that are listed here, something like 10 to the 11. And so this is where we can capture only a few neutrons before beta decay rates are competitive, and then beta decay will take over. On the much more exotic side, we have the R process, or the rapid neutron capture process. So this is happening very far from stability, where you can capture many, many generations of neutrons before beta decay will take over. And so this happens for much higher neutron densities, something like 10 to the 22. So these are our two sort of traditional neutron capture processes, but I really want to focus in on a third process known as the I process. So this is the intermediate neutron capture process. And it happens somewhere between the R and the S process for neutron densities that are something like 10 to the 15. And so just as a sort of cartoon example, I want to walk through these different nucleosynthesis, neutron capture nucleosynthesis pathways and sort of give different examples. And so if we imagine that we're in some sort of neutron-rich environment, we have our nucleus with Z protons and N neutrons. We capture a neutron to become one more unit neutron-rich. At this point, we can capture an additional neutron to become N+2, or beta decay can become competitive and sort of take over, and we can beta decay back towards the stable isotopes. So if we capture one neutron and then beta decay, This is sort of in a cartoon-like example, more similar to what you would anticipate seeing in the slow neutron capture process or the S process. If, on the other hand, we capture a couple of neutrons before beta decay sort of takes over, this is more similar to what you would expect to see in the I process or this intermediate neutron capture process. If, on the other hand, we're in a very neutron-dense environment, we can capture many, many neutrons before beta decay sort of takes over and there's this flux back towards stability. This is the R process or the rapid neutron capture process. But today, I'm really going to focus in on the I process that's happening only a few steps from stability. And to really highlight that the I process is a unique process that's not just some combination of, R and S process, I want to show this study that was done a couple years ago by Ian Roeder and collaborators. So this is looking at abundance versus atomic number for a metal poor star that's shown here. And the idea behind this study was to try to reproduce the observed abundances in this star, shown here by the black squares and then these open circles, using combinations of R and S process models. And so what you can see is that, for something like lanthanum up to lead, the R and the S, shown in red and blue respectively, is fairly robust at describing these overall observed abundances. But if we actually look in this region slightly lower in mass from germanium up to barium, you can see that combinations of the R process and the S process don't do a really great job at describing the observed abundances. But if we add this third process, the I process, that's unique from R and S, we're actually better able to describe the observed abundances in this region. So that sort of clues us in that, the I process is this third sort of unique process. So astrophysically speaking, where do we sort of see like the sites of the I process? So we have to have a neutron density that's something like 10 to the 15. And the I process is not actually new. It was actually proposed in the 1970s, but was revived recently to explain quote unquote strange abundances in certain classes of stars, such as post-asymptotic giant branch stars, carbon-enhanced metal poor stars, and rapidly accreting white dwarf stars. So sort of like the nitty-gritty details of each one of these stars and how they're unique from each other is not super important for the purposes of this presentation. What's actually important is that they have a similar sort of makeup, which is sort of shown in a cartoon here. And so they have this carbon-oxygen core, and then a helium layer, and then a hydrogen envelope. And so the way that we actually get neutrons in this sort of environment is through the carbon-13 alpha N reaction, which is very similar to the S process actually. And then our carbon-13 is replenished by carbon-12p gamma. And so we get our nitrogen-13 that then decays to carbon-13, which sort of is how we get this cycle. But in order for the I process to actually occur, what we need in simulations is convective mixing between the different layers. And so this is sort of how we can conceptualize the I process occurring. In terms of nuclear data needs, what we actually need is very similar to what you would anticipate needing for the R process or the S process. So this plot that I'm showing here is proton number versus neutron number. And this is just an example I process reaction network. And this is coming from the nucleosynthesis grid or NuGrid collaboration. And so the reaction flow that you can see here really is only a few steps away from stability. And so what that means is that for our nuclear inputs, the masses for the most part have been constrained. The beta decay half-lives and PN values have also been fairly well constrained for a lot of these nuclei. But what has not been well constrained is the neutron capture rates. And so what we really want to try to measure for the I process is a neutron capture reaction. But if we look globally across the nuclear landscape, this is taken directly from the NNDC, what we can see is that the number of neutron capture measurements that have been made are very limited, and they're very limited also to the stable isotopes. And so we have very few that are occurring on radioactive isotopes. And so then that sort of leads us to ask the question, why is this? And so how would you normally obtain an N gamma rate? You would want to do some sort of direct measurement where you have your neutron coming in, impinging on your A-1 target to create this A star nucleus that you want, in my case for the I process. But because we're dealing with radioactive nuclei, this A-1 target is prone to some sort of decay. It has a short half-life. The neutron itself is also not feasible for a target. And so what that means is that we can't really do direct measurements at this point in time for radioactive nuclei. So instead, we have to look towards indirect measurements that will allow us to access this same A-star nucleus through a different pathway. And so in this way, if you think about it, we can actually utilize the fact that there are short half-lives. And so there are actually a lot of different indirect techniques that you can use to constrain a neutron capture. There's the Oslo method, which utilizes charged particle reactions, Beta-Oslo, which I'm going to tell you about today, which utilizes beta-decay, the surrogate method, which uses dp gamma measurements as a surrogate for n gamma, and lastly, the gamma strength method, which utilizes gamma n measurements. But now that we sort of understand how we would go about measuring or obtaining these n gamma rates, how do we actually calculate neutron capture cross sections? So we have our neutron capture that would come into the statistical region, and what we use is Hauser-Feshbach theory for neutron capture. And so what Hauser-Feshbach theory says is that the neutron capture cross-section is proportional to three quantities: the nuclear level density, the gamma ray strength function, and the optical model potential. So these are the three things that we would need to constrain. The nuclear level density is the number of levels per MeV. The gamma ray strength function is related to the probability for a gamma ray to decay from a particular state in the nucleus. And then the optical model potential describes the relationship between this neutron and then your target nucleus. And so what we actually use in order to calculate these n gamma rates is a statistical reaction code like TALIS. And so the example that I'm going to show you today is for strontium-95 n gamma, which is fairly close to stability. Within TALIS, there are several different level density models that are available. And so if we want to see the impact of, looking at these different models and what that induces on the cross section, we end up with a plot that looks something like this, where you can see that the different level density models have this sort of variation for this reaction. We can actually do the exact same thing for the gamma ray strength function. And for this reaction, the 5 different models have an even wider spread. For the optical model potential, it's slightly less uncertain, but we anticipate that this would get worse as we go farther and farther from stability. And if we combine all 3 pieces of information, what we can see is that the overall uncertainty that's associated with the cross-section is something like an order of magnitude. And exactly this type of calculation that I've shown you is what goes into astrophysical sensitivity studies like this one, which is for the I process. So this is showing, again, our proton number versus neutron number for isotopes from cobalt up to technetium. And in this I process sensitivity study, what they were doing was actually the exact same TALIS calculations I just mentioned, where they're actually varying all the different level density models and gamma ray strength function models to figure out this maximum variation factor. And so this is the ratio between the lowest cross-section you get and then the highest cross-section that you get. And so what we can see is that there are a lot of these red boxes that are shown here, showing that they have this sort of very large maximum variation factor. And so I'll be looking today at these molybdenum isotopes, which don't have necessarily the highest sort of impact factor, but you can see that as we get farther and farther from stability, these are getting more and more uncertain. And so this sort of leads us to want to measure these and try to constrain them. And so the way that we do this at MSU, instead of using charged particle reactions to access the statistical region, is by using beta-decay. And so we populate this compound nucleus that we actually want to measure via beta-decay. And this enables us to actually be able to study nuclei that are very far from stability. And it's actually really feasible with low beam intensity, something like 1 particle per second. So the way that this would work is that you have your niobium-103 beam, for example, that then beta decays to molybdenum-103, that then allows us to constrain molybdenum-102 and gamma. So the 2 things that you actually need experimentally for this sort of technique is a radioactive beam and then a segmented gamma ray calorimeter. So this is what's called the Beta-Oslo method, and the Beta-Oslo collaboration was originally formed actually just a few years ago by Sean Liddick and Artemis Spiru at Michigan State, and then Cecilia Larson and Magna Guttormson at the University of Oslo. So now I want to give you sort of an overview of what the Beta-Oslo method is. So we're using beta decay to populate this nucleus that we're interested in. The 2 things we have to measure experimentally are the total excitation energy and then the gamma ray energy. From these 2 quantities, we can then extract our level density, which again is the number of levels per MeV, and our gamma ray strength function, which is the probability for a gamma ray to decay from a particular level in the nucleus. And then we have to apply some external normalizations. So for the Beta-Oslo method, we have 3 normalization points. We have the low-lying levels. This is taken directly from the NNDC from previously measured data. The level density at the neutron separation energy, which maybe you could take from previous data for things that are very close to stability, but far more likely we take from theory. And then lastly, the average radiative width or the giant dipole resonance extrapolation. By combining these pieces of information, we can then calculate our semi-experimental and gamma cross-section. So the exact same information, but shown sort of with pictures is here. And so from our experiment, we get our total excitation energy, we get our gamma ray energy. We construct this that we call the Beta-Oslo matrix. Excuse me, this matrix is sort of the raw matrix that we get directly from the experiment. The first step is that we have to account for the interaction of gamma rays in the detector. And so we have to unfold the detector response. And this is done with an iterative subtraction. The next thing that we do is isolate primary gamma rays. This is the first gamma ray emitted in every cascade. This gives us our probability matrix, capital P, that's then proportional to our level density and a transmission coefficient related to our gamma ray strength function. We then apply our external normalizations, the 3 things that I mentioned, before we can actually constrain our neutron capture cross-section in talus. So this is our sort of overview of how the Beta-Oslo method works. The segmented gamma ray calorimeter that we use for this technique is SUN, or the summing sodium iodide detector. It's a large size, high efficiency gamma ray detector that's a total absorption spectrometer. It's a 16 by 16 inch right cylindrical detector with a 45 millimeter borehole in the center for the beam to go through. It's composed of 8 segments of sodium iodide, where a segment corresponds to 3 PMTs, like this one that I'm showing here, and there are 24 PMTs in total. So summing across this detector gives us information about the total absorption or the sum spectrum, which gives us this total excitation energy. And then the individual segments, sort of you can think of as individual detectors, that then give us information about individual gamma rays. The resolution at an MEV is about 6%, and then the efficiency is about 85%. So let's talk about how total absorption works. I have this cartoon decay scheme that's shown here with different gamma rays de-exciting to the ground state. And so within a particular segment of SUN, or you can think of it as just an individual detector, what you would anticipate seeing is each individual gamma ray transition. But when you look at the SUN total, so you sum across the detector, what we actually have access to is the sum peak, which corresponds to this sort of entry state that we have here. So this is what we refer to as our TAS, or total absorption spectrum. And then this is our segment spectrum that measures or gives us our individual gamma rays. And the way that this actually looks inside of our Beta-Oslo matrix is that we have our excitation energy versus gamma ray energy, and each one of these gamma rays would fall sort of along this same excitation energy line. And so as a real world example, I'll show you cobalt-60. Cobalt-60 beta decays to 2 levels, and nickel-60. So we have these 2 gamma rays that de-excite that sort of have these characteristic energies. So in a particular segment of SUN, we would see our 2 gamma rays. And then in our total absorption spectrum, we see the sum peak that corresponds to about 2.5 MeV, the sum of these 2 gamma rays. And so now we have information both about our total excitation energy, as well as our gamma ray energy, which are the 2 things that we experimentally need to be able to measure. So the next thing that we need is our radioactive beam. And so the first measurement that I'm going to talk about is how we do Beta-Oslo at the NSCL using fast beams. So at the NSCL, beams were produced through the coupled cyclotron facility. And so we start with, in this case, a tin 124 beam that's accelerated through up to 120 MeV per nucleon. It then impinges on a beryllium-9 production target that's located here, and then fragments into everything that's lighter than the primary beam to some probability. We then utilize the A1900 fragment separator to purify the beam. The A1900 is composed of a series of quadrupole magnets, dipole magnets, and slits. So it sort of allows us to isolate the beam particles that we want to be sent to our end station. So we end up with a cocktail beam of yttrium, zirconium, niobium, molybdenum, and technetium isotopes that are then sent to the S2 vault. So they're coming down this way. They first pass through 2 silicon pin detectors shown here. These are used for our particle identification, and so they give us our energy loss and time of flight signal. After that, they continue down the beamline and they stop in a double-sided strip detector that's pictured here. And so this DSSD is composed of silicon. It's 1 millimeter thick, and it has 16 vertical strips and 16 horizontal strips on the front and back respectively that effectively allow us to create pixels and software so that we can correlate our implanted events with subsequent beta decays. And then surrounding the DSSD is the sun detector shown here. So the 2 cases that I'm gonna talk about first are niobium-103, which beta decays to molybdenum-103, giving us access to molybdenum-102 and gamma, and then the isomeric state in niobium-104, beta decaying to molybdenum-104, giving us the molybdenum-103 neutron capture. And so some information about the beta Q value and the separation energy are shown here. And so you can see that these are, for the Betaoslo method, really great candidates because the Q beta value and the separation energy are really similar. And information about the spins and parities and half-lives are also shown here. So the first thing that we do is correlate our implanted events. So our beam comes in, stops in our DSSD, which is sort of shown as this grid here. And then we correlate our implanted events with the subsequent beta decay, both in terms of where they are in pixels as well as in time. So we can extract our half-lives. And so these are the decay curves that are shown for the isomeric state in niobium-104. So you can see that the half-life that we extract is very similar to the half-life that we get from literature. We can do the same thing for niobium-103. So you see that the half-life is in fairly good agreement. And so the next step after this is to proceed into the Betaoslo analysis. And so we start with our raw matrix that's shown here. And the example that I'm going to show is for niobium-104. So we have excitation energy versus gamma ray energy. And so this is our total absorption coming from summing across sun, and then our gamma ray energy. And so this is our raw experimental matrix. So we get this directly from sun. So if you've seen one of these Betaoslo talks before, you might be thinking that this matrix looks a little bit sparse, especially up here in the statistical region. And that's kind of true. This was at this point in time, the highest mass case that we tried with Betaoslo, and also the lowest statistics case. But what you can see is that, there are some strongly populated levels at 2 and 3 MeV. That's consistent with known data. So we have verified that everything looks good. To start with our raw matrix, the next thing that we have to do is unfold this matrix to account for the detector response. So this is the same excitation energy versus gamma ray energy, but what's different now is that we've accounted for every single interaction of gamma rays at each excitation energy bin. So there's a response function for sun that's generated in JOUT4, and then we have an iterative procedure to determine what the incoming energy is of each different gamma ray. So this matrix represents, the raw matrix, but with the detector response accounted for. After we have our unfolded matrix, the next step then is to isolate primary gamma rays. So this is the first gamma ray emitted from each excitation energy bin. So this is also done with an iterative subtraction, where you start at the highest excitation energy bin and you make the gamma ray spectra and then subtract off weighted contributions of every other excitation energy bin. So this matrix that I'm showing here is what's called the primary matrix, and it's only filled with our primary or first generation gamma rays. So this matrix actually corresponds to this capital P probability matrix that's then proportional to our level density and then our gamma ray strength function. And so once we have this, we can then actually extract our level density and strength function in this region that's outlined here. So the level densities for molybdenum 102 and 103 are shown in these plots. And so level density shown here versus excitation energy. So experimentally, what we get from the first generation matrix are these points that are shown here. And so these data points, but we do have to use 2 normalization points to actually adjust the slope of these points. And so at the lower energies, we utilize known levels taken directly from the NNDC. And so that's what's shown by this sort of histogrammed region that's here. And so we match at the lower energies to our known levels. And then at the higher energies, we match at the separation energy We can't actually use data for this because we don't have any of these types of measurements. So instead, what we utilize are calculations. And so for this case, I'm using calculations from Stefan Gorielli, which are Hartree-Fock-Boguliev calculations that sort of allow us to calculate what the level density is at the neutron separation energy. So these are the level densities for molybdenum 103 and molybdenum 104. So the next thing that we need to get our neutron capture cross-section is our gamma ray strength function. But before we can actually do that, we have to account for the fact that we're using beta decay to populate the nucleus that we're interested in. Beta decay is a highly selective process, and so we have to do a spin reduction. And so for example, if we start with a 4- state, we assume allowed beta decay. That means we would be able to populate 3, 4, and 5. If we assume then that with those beta decays are followed by dipole transitions, then we restrict our spin range between 2 to 6 for the case of this 4-, and then from 1/2 to 9/2 of both parities for this 5-half state. And so using those exact same Hartree-Fock-Boguliev calculations from Gorielli's calculations, we can determine percentage of a level density populated as a function of spin. And so we see for the case of niobium 104, 51% population, and for niobium 103, 43% population. So we reduce our level density to account for the spin population, and then we can extract our gamma ray strength functions. So these are the gamma ray strengths. So we have gamma ray strength versus gamma ray energy for molybdenum 103 and 104. So these sort of have the very characteristic gamma ray strength function shape. And the third normalization point that I'm not showing here, but that we do is we extrapolate the tail of the giant dipole resonance, which is at much higher energies. And so this allows us to fix the overall magnitude of where this should lie along the y-axis. And so these are the two gamma ray strength functions for molybdenum 103 and 104. And I realized that maybe seeing them here, just side by side doesn't really have maybe a lot of meaning. And so what I want to show is that we can also compare this sort of systematically to previously measured Oslo data, as well as gamma ray strength function data. And so what I'm showing here is the gamma ray strength function versus gamma ray energy for Mali 96, 97, and 98 measured from two different techniques. So the Oslo data again uses charged particle measurements, and then the gamma ray strength function method utilizes gamma n measurements. And so they're color-coded with the same color for the same nucleus. And so the magenta that's shown here is for Mali 96. So you can sort of start to notice a trend. Mali 96 is shown here. And then for these purple boxes, Mali 97, that's shown here. And so you can see that the slope starts to increase as we increase mass number. And then once we get to the blue, which is Mali 98, you can see that the slope starts to increase even more. And so it has this sort of systematic way of the slope at higher energy sort of increasing as you go up in mass. And if I add my data onto this plot, you can see that it exactly follows the same type of trend. And so this is really exciting because it means we can actually compare radioactive nuclei that were measured with the Beta-Oslo method and sort of see the systematics from stable beam type measurements. And so this is really exciting. And so after we have our gamma ray strength function and our level density, we can then actually calculate the N gamma cross section in talus. And so I'm showing here the cross section calculated in talus versus neutron energy for molybdenum 102 N gamma and molybdenum 103 N gamma. And so if we actually do the same method that I talked about before, where we take all the different combinations of level densities and strength functions and calculate the overall uncertainty with the cross section, what we can see is that it's this sort of purple gray band that's shown here. So it's about an order of magnitude uncertain for both cases. But if we then insert the constrained level densities and strength functions from my data, we actually reduce this overall uncertainty to this like sort of light blue band that's shown here. So this is a significant improvement, and we can actually do the exact same thing for the reaction rate, which are used more often in astrophysics. So here I'm showing reaction rate versus temperature. And again, the darker purple band or the gray purple band that's shown here is sort of the default talus band. And then the blue band is the uncertainty that you get when you actually add in my experimental constraints. And I'm also showing here for comparison, the GINA React lib in this solid blue line, and then the purple dashed line is the Bruce lib libraries. So the next step after we have this is to actually try to insert these constraints into some sort of I-process calculation to determine the overall impact. And so we've done that. So this is very, very preliminary, like very much hot off the presses. We've formed a collaboration with the nucleosynthesis grid or NuGrid group. And these calculations were done by Andrea Clarkson, who's a graduate student at the University of Victoria. So this plot is actually showing the relative difference in abundance between my constrained rates and then the non-smoker or GINA React lib rates. And so this is very much hot off the presses, and we're still sort of trying to interpret what this means, but we see that there's quite a large relative difference in a lot of different isotopes. And so these results seem very promising. And we're also in the process of trying to compare with abundances in carbon enhanced metal poor stars. So this is sort of the first half of my presentation where we talked about, I-process constraints that we can get from the NSCL. But I also want to say that the molybdenum isotopes are not the only things that are important for the I-process. But in a recent sensitivity study that was done by the same group, the NuGrid group, for a slightly higher mass region, this is sort of showing reaction flow for these isotopes that are here. And so in these sort of sensitivity studies, very similar to what I showed before, the reaction that had the highest overall maximum variation and uncertainty was actually barium-141 and gamma. And very fortunately, we actually were able to measure this with a different campaign of experiments at Argonne National Laboratory. And so we took Sun to Argonne to utilize Caribou, which is the californium rare isotope breeder upgrade, which is where we can get californium-252 fission fragments delivered out into the low energy area where we have Sun set up. And so Sun is set up out here. So here's some photos of what it looked like in action. We actually moved Sun to Argonne with the associated tape station shown here in November of 2019. We did our first commissioning measurement, which ended up being really important for the I-process, barium-141 and gamma. And then we did another experiment that's the thesis project of Kaylee Harris, and that's krypton 87 to 89 and gamma, which is also very important for the I-process. We had a lot of other things, other experiments that we want to do at Argonne, but they were delayed due to COVID, so we're hoping to get back there soon and do that. But the Caribou beams are delivered down this way and into Sun. So now I'm going to talk about the different detector components that we have that are very different from what we used at the NSCL. And so the first thing is that we have our beta detector is actually a fiber detector, what's lovingly called by the graduate students sunspot, which is the scintillating plastic optical transport detector. And so it's 8 panels of scintillating plastic that are shown here in the white. And then each one of these panels has 4 fibers attached to it. And so 2 go to one PMT and 2 go to the other PMT. And then these PMTs, of course, give us our beta signal. And so this is how we can make sure that we have a beta decay there. And so this is our detector that we sort of use in place of the DSSD. And this was actually designed and developed by Hope College. So in addition to our beta detector, we also have a different setup where we use a tape station called Suntan, which is the tape system for active nuclei. And so this so far has been used for I-process type studies and then nuclear security studies. And so Suntan is a tape station. So we have Sun that's here, and then our beta detector, this fiber detector that's sort of around the tape arm. And so the tape station is this box, and it has a movable tape that sort of gets put up and into the path of the beam. And so it effectively becomes the target at the center of Sun. So the beam comes in this way and implants on our piece of tape. We accumulate data for a certain period of time, depending upon the half-life of the isotope and then the daughter. We then turn off the beam, observe the beta decay, and then we move this contaminated piece of tape out of the way and into tape storage, where a fresh piece of tape comes up and the process sort of repeats. And so tape stations are really ideal for these types of measurements where the parent has a much shorter half-life than like the long-lived daughter component. So just as an example, the commissioning run that we actually did was cesium-142 beam, beta-decaying to barium-142, that then allows us to constrain this important reaction for the I process, barium-141 and gamma. And so you can see what I mean about the difference in half-lives. And so cesium half-life is 1.6 seconds, but the barium half-life is 10 minutes. And so there's actually not really a way to be able to do this type of measurement using the DSSD setup, because you wouldn't be able to correlate these very effectively. So in terms of what the data actually looks like, showing here counts versus time. And so this is a tape cycle where we accumulate for 30 seconds, observe the decay for 5 seconds, and then move the tape out of the way. And so that's what this looks like. So we're accumulating for 30 seconds, turn the beam off, observe the decay, and then we move the tape, accumulate for 30 seconds, stop the beam, decay, move the tape, and so on. And so then we can stack these sort of growth and decay curves on top of each other to get things like the half-life, and then to construct the Beta-Oslo matrix that looks like this. And so this is preliminary as well, but you can see that the relationship between the Q beta and the separation energy is also quite good for this case. So this is the matrix that we got online during the measurement. And so there are a lot more statistics in this matrix than the previous one. And so that's always nice. And so I'm working on this data right now, but very preliminarily, the level density and strength function look really promising. So if we look first at the level density, what we can see is that already, even without doing like the full, rigorous background subtraction and everything like that, we can see that the known data, which is sort of these points that are, or these solid lines that are shown here, match up pretty nicely with the observed, the data that we're taking from the Beta-Oslo method. And so already these results look really promising. And so we're really excited to sort of take these results and then apply them to the I process. So today I've told you about I process nucleosynthesis and how it's really dominated by neutron capture cross sections. We talked about the Beta-Oslo method for constraining neutron capture reactions, and then discussed experimental campaigns both at the NSCL as well as at Argonne National Laboratory. We have this amazing collaboration with the New Grid group that's going to allow us to determine the impact of our constrained cross sections for the I process reaction network. Definitely don't want to end this presentation without saying that the future is really bright for Beta-Oslo type studies at the at EFRIB. And so the Beta-Oslo technique, as I mentioned before, only needs beam rates of something like 1 particle per second. And so what this means is that in this sort of yellow region, we'll actually be able to measure some Beta-Oslo for our process type nuclei, which is something that hasn't been done before. And so we're really excited to start applying this technique at EFRIB as well. So these are all of the collaborators that were involved in these different projects. Special thank you to Sean and Artemis for mentoring me over the last few years. It's been very great. And I also want to say thank you to the Nuclear Science and Security Consortium who funded all of this work. And lastly, I'd like to say thank you to everyone for listening, and I'm happy to take any questions.
You can imagine a standing ovation. Thank you very much for a beautiful talk, Andrea. Really appreciate it. The floor is open for questions. So if you want to raise your hand or ask the question directly to Andrea, please go ahead. Maybe I can start, Andrea. Oh, there we go. Alexander, please.
Hi, Andreas.
Hi.
Yeah, good talk. Thank you. I'm just curious. Would like to ask a general question about Beta-Oslo method. How do you see what's the main problem of Beta-Oslo method? Where the systematic uncertainties coming from, and what are you going to do with that in the future?
Yeah, that's a great question. So, I think that with the Beta-Oslo method, what we all sort of recognize as being like maybe a limitation would be the fact that we have to use a lot of external normalizations. And so that's something that we're constantly working on. And so we actually have a paper that's out right now to try to do normalizations using different sorts of techniques that don't rely on previous data or on theory calculations. And so I think that probably is the biggest weakness. And so we're sort of trying to address that by finding new ways of analyzing the data that will sort of get around these normalizations.
Actually, along the lines of Alexander's question, so if I understood the strength function, you normalize to the giant tail.
That's right.
So if you don't know the giant tail, how do you normalize it?
Yeah, that's a good question. So for the nuclei that I actually showed, we don't have measurements of like the giant dipole data, but we look in terms of systematics for things that have been measured before and sort of get that normalization from, nuclei that are like the nearest isotone, isobar, like things like that. But as we go farther from stability, that will become a problem. And so we have to really work on the normalizations quite a bit.
Thank you. I'm checking. Any more questions or comments for Andrea?
I have one, but I can't find the raise hand thing. Sorry about that.
Yeah, go ahead, Charlie.
Let's see. So for sunspot, what kind of threshold do you guys have on that for the betas?
I don't know off the top of my head, but we do have to set it fairly high because the fibers are pretty noisy. And so we have a new postdoc actually who's working on trying to do like maybe a silicon photomultipliers instead of doing like the larger PMTs.
Okay, yeah, that makes sense because the fiber transmission has got to be really small.
Yeah.
In terms of the light emitted, and that just raises your threshold. To me, it seems very high. So
yeah,
but just a question. Thank you.
Absolutely.
Artemis.
Yeah, this is just to add. Yeah, Andrea hasn't been much involved in this study, but the threshold is roughly 300 kV right now.
I have one technical question. Sorry for the ignorance here, but so when you do the unfolding, you said you use a GN response. I would imagine that GN response you have benchmarked with sources. Okay.
That's right. Yeah, the sun GN has been benchmarked with sources. Yeah.
So if you unfold, say, the cobalt spectrum, you get what you put in.
Yes. Yeah.
Okay. Any more questions for Andrea? Comments? Seems like you made a very clear presentation, Andrea, which I think is the case. And so if there is no more questions, oh yeah, sure. Let's give a virtual applause and thank you so much, Andrea. Beautiful talk and all the best to you in the future. Huh?
Thank you.
And all the best to all. And Andrea, you want to stay a little?
Yeah, absolutely.
Yeah, that was very nice, Andrea. There was I think it was a record attendance.
Oh, that's good.
Registered 82 participants.
Oh, okay, nice.
I'll share with you the list in a keep screen capture form,
okay.
Because I haven't figured out how to actually make a list of the participants. Although there will be the video, and you can look at it and probably find out. But it was very, very good.
Yeah, that was really nice, Andrea.
Oh, thank you.
Yeah, you learn well from Heather.
That's true.
Very
Yeah,
good, very-
that's very true.
No,
Um,
all you.
no, this was very nice, and you know, one of the, shall I say, one of the problems that I always have with some of these proposals or talks is the actual motivation, which we all understand. I mean, but you made it very clear why these measurements are important. I mean, it's not just, yeah, we don't know by a factor of 100 the cross section, but you know, so who cares if it doesn't change anything? But here,
Right.
you made it very clear. So thank you.
Yeah, absolutely.
Okay, well, in that case, if you send us the talk, I will post it. Well, I will ask Ryan to post it, and then this is a very technical question, but I always have problems.
Okay.
Could you put the slides again?
Yeah, absolutely.
Okay, so you're still recording, you know that, yeah?
Ah, well, this is a secret recording. Sorry. Let me stop it. We don't want to.